There is a machine drifting through interstellar space right now, and the void out there isn't killing it. Voyager 1 crossed beyond the Sun's protective reach in 2012 into a bombardment of galactic cosmic rays, heavy atomic nuclei hurled from dying stars, each one carrying enough energy to tear through solid metal. Voyager doesn't care. It has no cells to destroy, no mind to unravel, and no lungs to fail. It is the perfect traveller for this environment, precisely because nothing inside it is alive. Now place human beings in that same vessel, and everything that made Voyager immune becomes a death sentence. Those same particles begin shredding DNA day after day, with nothing capable of stopping them. Systems clog, with no replacement parts on the way. Air recyclers inch toward breakdown. One degraded component is enough to change everything. And here is what almost nobody says out loud. Getting a ship to another star might be the simpler half of the challenge. Keeping the people inside it alive is the part we haven't even come close to solving. If you enjoy this type of content, consider liking and subscribing to the channel. It truly helps me. Now get comfortable. Let's begin. Light leaving the Sun right now will reach the nearest star in 4 years. A human being walking at normal pace toward that same star would arrive in roughly 870 million years, assuming they didn't stop to sleep. That gap between light and footsteps is the problem of interstellar travel in a single image. The distance is so extreme that even our fastest spacecraft, the ones we have actually built and launched, would take tens of thousands of years to complete the crossing. Voyager 1, the most distant human-made object in existence, has been travelling for nearly 50 years and has covered less than 0.003% of the distance to the nearest star. We are, by any honest measure, nowhere near capable of crossing interstellar distances. And yet the conversation about how to do it has been running for decades, filling books and documentaries and conference halls with proposals, calculations, and competing visions of humanity's interstellar future. Almost all of those conversations are about the same thing: propulsion. How fast can we go? What kind of engine could get us there? Whether fusion drives, laser sails, antimatter rockets, or nuclear pulse engines represent the most promising path forward. These are the questions that dominate the field, that attract the funding, that generate the headlines. And they are all, in a very specific and very important sense, focused on the wrong problem. Not because propulsion doesn't matter, it matters enormously. Crossing interstellar distances requires generating energy outputs that dwarf anything humanity has ever produced, sustained over timescales no engine has ever operated, aimed with precision no navigation system has ever demonstrated. The propulsion problem is real, it is unsolved, and it deserves every serious mind working on it. But propulsion is only half the problem, and it is the easier half. Here is the assumption that almost nobody states out loud, because it feels too obvious to need stating, that if you solve propulsion, the mission is essentially complete. Build a fast enough engine, accelerate a ship to some meaningful fraction of the speed of light, aim it at the nearest star, and arrival equals success. The hard part was getting the ship moving. Once it's moving, you just wait. This assumption is wrong, because the moment a ship reaches interstellar space, the propulsion problem ends, and what replaces it is not a single new problem. It is hundreds of simultaneous compounding, interacting problems that all get worse over time, with no external help available, no resupply coming, and no margin for the kind of errors that in any other engineering context would simply be called the cost of doing business. Think about what propulsion actually solves. It answers exactly one question: how do we cross the distance? It has a defined success condition. The ship either reaches the target velocity or it doesn't. It has measurable progress. Every test firing, every design iteration, every incremental improvement in fuel efficiency moves a visible needle in a visible direction. Engineers understand this kind of problem intuitively. It has edges. It has a finish line. It is the kind of hard that, however enormous, fits inside a framework humans know how to attack. Survival does not have a finish line. There is no moment where the crew crosses a threshold and the problem is solved. There is only the next hour and the next day and the next year, each one requiring that every system aboard continues to function within tolerances that grow tighter as reserves deplete and components age. The survival problem is not a wall you break through. It is a current you swim against indefinitely in water that gets colder the longer you're in it. The moment a ship passes beyond practical resupply range, which for any realistic interstellar mission is within the first few weeks of departure, it becomes a closed system. Nothing new enters from the outside. Nothing broken gets replaced from the outside. Every resource the mission will ever have was loaded before departure. Every failure that will ever occur must be resolved from within, and from that moment, one clock begins running that never pauses and never resets. The clock measuring how much of the ship's finite reserves have been spent, how many of its components have moved one day closer to their operational limits, and how many of its margins have narrowed since yesterday. To survive inside interstellar space, a ship must simultaneously and continuously accomplish something that no human engineering project has ever achieved. It must recycle its air with near-perfect efficiency for decades, with no replacement parts arriving from outside. It must recover its water at a rate close enough to 100% that the cumulative loss over half a century doesn't drain the supply, and it must do this with membranes and pumps and sensors that are themselves slowly degrading. It must grow or preserve enough food to sustain a crew across timescales that exceed the shelf life of any stored nutrition system ever designed. It must manage waste, regulate temperature, generate oxygen, maintain structural integrity, power every system continuously, and keep the human beings inside it physically healthy and psychologically functional. Not for the months that current space missions demand, but for decades or centuries with no pause, no relief rotation, and no possibility of calling for help. Every single one of these requirements is an unsolved problem at interstellar timescales, not a partially solved problem awaiting a final breakthrough. An unsolved problem, one where the best performance ever demonstrated falls so far short of what the mission demands that the gap between them is not an engineering challenge. It is a different category of difficulty entirely. The public imagination fixes on departure because departure is dramatic. A ship accelerating away from Earth, engines blazing, aimed at a point of light 4 light years away. That image has weight, momentum, emotional power. It tells a story of courage and ambition, and the irrepressible human drive to go further. Propulsion research gets to live inside that image. Every breakthrough feels like progress towards something epic. But the real story of an interstellar mission would not be the departure. It would be the 10,000th morning inside the same cabin, with the same recycled air, the same faces, and the same growing list of systems that are running slightly below specification. It would be the moment somewhere around year 20 when the crew realizes that the water recovery rate has declined for the 3rd consecutive year, and there is no procedure in any manual for reversing the trend. It would be the quiet conversation in year 35, held in whatever passes for a private space aboard the vessel, where 2 crew members try to decide how to tell a third that the cognitive tests they've been running every 6 months show a pattern that doesn't look like normal aging. None of these moments are cinematic. None of them would make a good trailer. They are the quiet, grinding, unglamorous reality of what it means to keep a closed system alive inside an environment that is constantly working against it. And they are the reason why surviving interstellar space is a harder problem than reaching it. Because reaching it is a problem you solve once, at the beginning, in a blaze of fire and ambition. Surviving it is a problem you solve every single day for the rest of the mission, with tools that are wearing out and a crew that is slowly being changed by the journey in ways nobody fully understands yet. There is a clean way to frame the difference. Propulsion is like climbing a mountain, brutally hard, genuinely dangerous, demanding everything you have. But it has a summit, and when you reach it, that particular ordeal is over. Survival is like maintaining a city built on the side of that mountain, after the climbing team has gone home and the supply roads have washed out and the weather has closed in permanently. The mountain gets summited once. The city has to keep running forever, with whatever was inside it on the day the roads closed. The ship must be its own planet. It must carry every resource it will ever need, manufacture every replacement it will ever require, heal every injury it will ever sustain, and hold together every human relationship that keeps its crew functional. All of this simultaneously across timescales that no closed system in human history has ever been asked to survive. The engine gets you there, everything else keeps you alive, and everything else is harder. That is the truth that almost no conversation about interstellar travel starts with. It is the truth this one is built around. Step outside on a clear night and look up. Every star you can see exists inside a kind of cosmic weather system, a vast bubble of charged particles blown outward by its host star, carving a protected zone through the surrounding galaxy. Our sun creates one of these bubbles. We live inside it. We were born inside it. Every human being who has ever existed has spent their entire life inside it, and we have absolutely no idea what it feels like to leave it, because nothing alive ever has. The bubble has a name, the heliosphere. The sun constantly blasts charged particles outward in every direction, a stream called the solar wind, and this wind inflates a magnetic shield around our entire solar system, stretching roughly 18 billion kilometers from the sun in every direction. That shield does something quiet and invisible and absolutely essential. It deflects a significant portion of the galactic cosmic radiation that floods the rest of the Milky Way. Inside it, we are partially protected from the galaxy. Outside it, we are not protected at all. Voyager 1 crossed that boundary in August of 2012. The moment it did, its instruments detected something immediate and unambiguous. The density of galactic cosmic rays spiked sharply. The heliosphere had been suppressing incoming radiation by roughly 20 to 50% depending on solar activity cycles. Outside its boundary, that suppression vanished entirely. The full, unmodulated flux of the galaxy poured in. Voyager didn't notice. It has no cells. It has no brain. The radiation passed straight through its metal body and changed nothing that mattered. A human crew would have noticed immediately, and the noticing would never stop. But here is what almost never appears in public discussions of interstellar travel. The heliosphere is not the only boundary a departing ship must cross. It is not even the most time-consuming one. Beyond the heliosphere lies the Oort cloud, a vast, loosely defined shell of icy bodies and frozen debris left over from the formation of our solar system, extending outward to perhaps 100,000 astronomical units from the Sun. Its outer edge sits approximately 1.5 light-years away. At 5% of the speed of light, a departing ship needs roughly 30 years just to clear this region. At 1%, closer to what near-term propulsion concepts might actually achieve, the crossing takes 150 years. This means the journey to the nearest star is not a single leap across 4 light-years of open void. It is a decades-long exit from our own solar neighbourhood, already beyond radiation protection, already accumulating damage, already burning through resources, before the true interstellar crossing has even begun. The survival clock doesn't start at some dramatic midpoint between stars. It starts the moment the ship passes beyond practical resupply range, which is within the first few weeks of departure. Everything that follows, every failure, every repair, every depleted reserve, flows from that single irreversible moment. Now consider what the interstellar medium actually is. The physical substance of the space between stars that the ship will spend most of its journey moving through. It is not empty. It is a thin gas of hydrogen and helium, threaded with dust, laced with magnetic fields, and saturated with radiation from every violent event the galaxy has produced over billions of years. Supernovae, neutron star collisions, black hole jets. This radiation, the galactic cosmic rays, includes fully ionized nuclei of heavy elements, iron, silicon, oxygen, traveling at substantial fractions of the speed of light. A single iron nucleus at these energies carries the kinetic punch of a fast baseball, concentrated into a space smaller than an atom. These particles do not behave like the radiation most people picture when they hear the word. X-rays and gamma rays scatter energy broadly and damage tissue in ways the body has some capacity to repair. Heavy ions are different. When a high-energy iron nucleus strikes biological tissue, it cuts a track of destruction through every cell in its path, shattering DNA along a line so dense with damage that the cell's repair machinery often cannot reconstruct it. When the same particle strikes spacecraft materials, it displaces atoms from their crystal structure, weakens polymers, degrades electronics, and accumulates invisible damage that no amount of maintenance can undo. The radiation is not a hazard that peaks and fades, it is a constant in every direction for the entire duration of the transit. The interstellar medium itself becomes a weapon at high velocities. Even at 5% of the speed of light, roughly 15,000 kilometers per second, every hydrogen atom the ship encounters hits the hull with the energy of a low-grade cosmic ray. At 10% of light speed, the energy per particle climbs into ranges that produce secondary radiation showers inside the hull material itself, as incoming particles fragment against the structure and scatter in every direction. This creates one of the most vicious paradoxes in all of interstellar mission planning. Travelling faster reduces the total trip duration, which sounds like it should reduce the survival burden, but it simultaneously increases the radiation intensity striking the vessel at every moment. You cannot outrun the problem. Every knot of speed you gain tightens the trap from a different direction. Temperature adds another layer of hostility that operates on a different timescale but with equal relentlessness. Interstellar space sits at roughly 2.7 Kelvin, barely above absolute zero. At this temperature, radiating waste heat into the surrounding void is the only available cooling mechanism for the ship's systems. There is no atmosphere to carry heat away. There is no nearby thermal mass to absorb it. The ship must manage every watt of thermal energy it produces internally, balancing the heat generated by its power systems, life support machinery, electronics, and human bodies against the radiation of that heat into a void that offers no buffer. Drift too far in either direction, and temperatures inside the habitat move toward conditions that kill equipment, crew, or both. The void does not negotiate. What all of this means, taken together, is something that changes the entire architecture of how an interstellar mission must be conceived. The ship is not a vessel transiting between 2 points. It is a sealed world moving through an environment that is actively, continuously, and simultaneously hostile to its structure, its systems, and every biological organism inside it, from the moment it departs to the moment it arrives, with no pause, no shelter, and no mercy anywhere along the way. The propulsion problem ends at ignition. The environment problem never does. In 1998, the first module of the International Space Station was launched into orbit. Over the following years, it grew into the most complex structure humanity had ever assembled in space, a gleaming lattice of solar arrays and pressurized modules circling Earth at 28,000 kilometers per hour. From the outside, it looks like a triumph of engineering permanence. From the inside, it looks like something else entirely, a repair shop that happens to be in space. The crew members aboard the ISS are mechanics first and scientists second. A significant portion of their working hours, far more than mission planners originally budgeted for, is spent diagnosing faults, swapping components, cleaning filters, tightening connections, and coaxing aging hardware back to operational status. This is not a failure of design. It is what happens when complex systems operate continuously inside a hostile environment. And every piece of data collected from 25 years of station operations tells us exactly what would happen to a vessel attempting the same feat across interstellar distances. Except the distance is measured in light years instead of kilometers, the mission duration is measured in decades instead of months, and the supply ship is never coming. The station's most critical set of systems is its Environmental Control and Life Support System, ECLSS, responsible for providing breathable air, drinkable water, stable temperature, and manageable humidity for the crew. It is the systems that, if it fails, kills everyone aboard within hours or days. A study analysing crew time records from the station's early operational years found that actual maintenance demands on these life support systems exceeded the original design estimates by approximately one order of magnitude. Not double, not triple, 10 times more crew time than the engineers predicted. And the failures driving that overrun weren't exotic. They were the ordinary grind of pumps wearing out, filters clogging faster than expected, seals degrading in ways the models hadn't fully captured. The station survives this maintenance burden because it has a supply chain. Spare parts arrive on cargo vehicles, failed units get replaced with fresh hardware launched from Earth. Crews rotate every 6 months before fatigue and confinement degrade their performance too severely. The ISS is not reliable enough to run without intervention. It simply has intervention available whenever it needs it. That distinction is everything. Remove the supply chain, remove the rotation schedule, remove the ground support team, and the station's operational model collapses entirely. What remains is a collection of aging systems with no relief in sight, held together by whoever is aboard with whatever is left on the shelves. That is precisely the situation an interstellar crew would face, except they would face it from day one, and it would get worse every year. Water recovery illustrates the problem with painful precision. NASA achieved 98% water recovery aboard the ISS in 2023, a genuine engineering milestone, the result of decades of refinement and the addition of a brine processor assembly that extracts water from waste the original system discarded. 98% sounds nearly complete. It sounds like a closed loop. It is not. For every 100 litres of water entering the cycle, 2 litres are lost as residue, system inefficiency, or unrecoverable waste. On the ISS, those 2 litres are replaced by water delivered from Earth on the next resupply mission. The loop doesn't actually close, it leaks, and the leak is filled from the outside. An interstellar vessel cannot fill the leak from the outside. Those 2 litres must come from somewhere else, or they are simply gone. For a crew of 20 cycling several hundred litres per day through drinking, food preparation, agriculture, and waste processing, a 2% loss compounds to over 100,000 litres across a 50-year transit. Roughly 100 tonnes of water mass that must be loaded at departure on top of the operating supply just to cover the leak. Extend the mission to 100 years and the deficit doubles. The arithmetic is punishing even before you account for the fact that 98% recovery is humanity's best demonstrated rate, achieved under ideal conditions with fresh components, continuous resupply, and ground engineers monitoring every parameter in real time. Because recovery efficiency doesn't stay at 98%, it degrades. the distillation membranes that separate clean water from contaminants gradually foul with mineral deposits and biological films. The catalytic systems that break down organic contaminants slowly lose their active surface area. Sensors drift out of calibration, pumps wear, seals age. Each degradation pathway shifts the system from 98% toward 95, toward 92, toward 88, and every percentage point lost accelerates the daily deficit. The water doesn't disappear in a dramatic rupture. It bleeds away, invisibly, 0.01% at a time, until the shortage becomes impossible to ignore and impossible to reverse. This degradation curve applies to every closed-loop system on the vessel: air recycling, waste processing, food production, thermal regulation. All of them experience the same relentless drift toward lower efficiency. Engineers call this phenomenon the closure gap, the difference between the theoretical perfect recycling rate and the actual achievable rate under real operating conditions over time. On short missions, the gap is manageable. On missions measured in decades, the gap is a death sentence unless something actively closes it. And there are only two theoretical options: either improve recycling efficiency beyond anything ever demonstrated, or extract raw materials from the interstellar medium during transit. The interstellar medium contains roughly 1 hydrogen atom per cubic centimetre. Collecting useful quantities from this near-perfect vacuum at any plausible transit speed would require electromagnetic ram scoops of such enormous scale and energy consumption that they remain firmly in the domain of theoretical speculation, which leaves the crew with the first option and no demonstrated path to achieving it. The loop leaks, the reserves drain, and the rate of draining accelerates as the components responsible for closing the loop wear down from the inside. Spare parts compound the problem in a way that strikes at the very foundation of mission architecture. NASA's reliability engineers have concluded that achieving acceptable reliability for missions where resupply is impossible requires carrying spare components with a total mass approximately equal to the original system mass. To sustain one life support system across a multi-decade mission, you need to carry roughly 2 of them, one operating, one waiting in pieces on the shelf. That doubling applies to every critical system aboard: life support, power, thermal control, navigation, communication. Double the mass of each before accounting for propellant, crew provisions, or habitat volume. And then the rocket equation takes over. The relationship between payload mass, propellant mass, and achievable velocity is exponential, and at interstellar speeds, the exponent is merciless. Small increases in payload mass produce enormous increases in required propellant. More propellant requires a larger engine. A larger engine requires stronger structure. Stronger structure requires more spares. The ship spirals toward masses so large that no conceivable propulsion system could accelerate them to useful interstellar speeds. The spare parts needed to keep the crew alive make the ship too heavy to reach the speed required to get them there in the first place. Some mission architects propose in situ manufacturing as the escape from this trap, equipping the ship with fabrication tools capable of producing replacement parts from raw feedstock during transit. 3-dimensional printing using metal and polymer feedstock could theoretically produce replacements for a subset of failed components. But fabrication requires energy, raw materials, and equipment that itself degrades and requires maintenance. The printer's components have finite lifetimes. The feedstock supply is finite. The precision achievable by onboard fabrication may be insufficient for the components that matter most: pressure vessel walls, high-speed bearings, electronic circuit boards. And there are categories of replacement that no onboard fabrication system can address. You cannot 3-dimensionally print a new semiconductor chip from generic metal powder. You cannot print a new catalytic membrane substrate. You cannot print the specialized cryogenic seal material that just failed in the cooling loop at 2 in the morning on year 23 of the mission. What the ISS data ultimately reveals is not a set of problems specific to that particular station. It reveals the fundamental character of complex systems operating in hostile environments over time. They do not fail suddenly and completely. They degrade continuously and incrementally, demanding more maintenance as they age, consuming more resources as their efficiency falls, and narrowing the margins available to absorb the next failure. The ISS manages this character through resupply and rotation. An interstellar vessel must manage it alone, with a fixed inventory that was fully loaded at departure, and a crew that is itself subject to the same degradation processes as every other system on the ship. The station survives because Earth is 400 kilometers below it. An interstellar vessel must survive because nothing is anywhere near it. That difference is not a difference of degree, it is a difference in kind, and it is the difference that turns a maintenance problem into an existential one. In the basement of Brookhaven National Laboratory on Long Island, there is a machine that scientists use to simulate the inside of interstellar space. It accelerates ions, iron, silicon, oxygen, to energies representative of galactic cosmic rays, then fires them through biological samples to measure what happens. The results, accumulated over more than a decade of NASA-funded research, are some of the most sobering findings in the entire field of space medicine, and they receive a fraction of the public attention given to rocket engines. The reason they matter is this: the radiation environment outside the heliosphere is not merely a hazard to the ship's structure and electronics. It is direct, continuous, physically measurable assault on the tissue of every human being aboard. Not an abstract risk to be managed with scheduling and monitoring, a biological process that begins the moment the ship crosses beyond the heliosphere's protection and does not stop until the mission ends, or the crew does. Annual radiation exposure in interstellar space is estimated at roughly 400 to 600 millisieverts from galactic cosmic rays alone. A 6-month stay aboard the ISS typically produces a cumulative dose of 80 to 160 millisieverts, and the station sits inside Earth's magnetic field, which deflects a significant portion of the most dangerous particles before they ever reach the hull. Outside the heliosphere, that magnetic protection is gone. The full, unmodulated galactic flux pours through the ship's walls continuously. Over a decade of interstellar transit, cumulative exposure climbs into ranges that substantially elevate lifetime cancer risk and begin approaching thresholds associated with measurable acute effects during periods of elevated solar activity. But cancer, for all its severity, is a long-term risk. It operates on timescales of years and decades. The more immediately mission-critical danger from galactic cosmic radiation is something subtler, faster, and in some ways far more frightening: what it does to the brain. The heavy ions that make up the most damaging component of galactic cosmic radiation, particularly iron nuclei travelling at energies exceeding 1000 mega-electron volts per nucleon, interact with neural tissue in ways that no other common radiation source replicates. Lower energy radiation like X-rays tends to cause scattered single-strand DNA breaks that the cell's repair machinery can often address. Heavy ions cause clustered damage, multiple simultaneous breaks in both strands of the DNA helix, along with destruction of the surrounding repair proteins. The cell cannot reconstruct what was there. It either dies or survives with corrupted instructions. In most tissues, cell death is the more manageable outcome. In the brain, where neurons are largely irreplaceable, and the architecture of their connections encodes everything the crew knows and can do, the damage accumulates differently, not as a sudden wound, but as a slow, structural unravelling that no medical intervention aboard the ship can reverse. Researchers at facilities including the NASA Space Radiation Laboratory exposed rodents to charged particle doses at energies representative of the galactic cosmic ray environment. The results were consistent across multiple independent studies. Irradiated animals showed significant and persistent deficits in spatial memory, the ability to navigate physical environments. They showed impaired episodic memory, degraded recognition memory, and reduced executive function. The higher-order cognitive processes responsible for planning, decision-making, and behavioral flexibility. They also showed altered fear extinction. Their ability to learn that a previously threatening situation was no longer dangerous was compromised, leaving them in a state of elevated, persistent anxiety that did not resolve on its own. Under microscopic examination, the neural basis of these deficits was visible. Irradiated animals showed significant reductions in dendritic complexity in the medial prefrontal cortex, the brain region most critical for decision-making and impulse control. Dendrites are the branching extensions of neurons that receive signals from other cells. When their complexity is reduced, the neuron's ability to integrate information from multiple sources is degraded. The irradiated animals also showed reduced spine density along those dendrites, fewer synaptic connection points, meaning a physically thinner communication network woven across the entire brain. Additionally, researchers observed persistent neuroinflammation. Microglial cells, the brain's resident immune cells, became chronically activated and began releasing inflammatory molecules that further damaged surrounding neurons. This inflammation did not resolve after exposure ended. It persisted for the animal's entire remaining lifespans. That last detail carries a specific and devastating implication. The damage is not temporary. There is no recovery phase after the mission, during which the crew's cognitive function returns to baseline. The radiation accumulates in neural tissue continuously, and the changes it causes are permanent. Every day of transit is a day of irreversible neurological change. The crew that arrives at the destination, if they arrive, will not think as clearly, remember as accurately, or make decisions as soundly as the crew that departed. And the degradation will have been building, invisibly but measurably, for every year of the journey. What makes this particularly cruel is the specific nature of what is being lost. The faculties most damaged by heavy ion radiation, executive function, working memory, spatial reasoning, the ability to learn new information and adapt to novel situations, are precisely the faculties the crew needs most to keep the ship alive. Diagnosing an unfamiliar failure mode in a system the manual no longer fully describes requires executive function. Navigating a repair inside a cramped equipment bay without making a secondary error requires spatial reasoning. Adapting a procedure designed for a component that no longer exists to one that does requires flexible problem solving under pressure. The radiation is not damaging peripheral functions while leaving the mission-critical ones intact. It is targeting, with brutal precision, the exact cognitive toolkit that stands between the crew and the ship's slow collapse. Shielding against this radiation is the obvious response. It is also far harder than most people assume, for a reason that cuts against every instinct. When lower energy radiation strikes a dense shielding material like aluminum or steel, the material absorbs the energy and the threat is reduced. When high-energy galactic cosmic ray particles strike the same dense material, something different happens. They fragment. The original heavy nucleus breaks apart and produces a shower of secondary particles, neutrons, protons, lighter ions, that scatter outward in every direction, including inward toward the crew. In many configurations, adding more dense shielding does not reduce the dose received by the people inside. It increases it. The shield becomes a particle multiplier. The wall meant to protect the crew becomes a source of additional radiation. Effective shielding against galactic cosmic rays requires either enormous thickness of low density, hydrogen-rich material, on the order of several meters of water or polyethylene surrounding the entire pressurized habitat, or active magnetic shielding using superconducting coils to deflect charged particles before they reach the hull. Both approaches carry mass penalties so severe they feed directly back into the propulsion spiral. Several meters of water shielding around a habitat module adds thousands of tons to the vessel. Active magnetic shielding requires superconducting magnets, cryogenic cooling systems, and continuous high-power input, all of which add mass, complexity, and their own maintenance burden. No practical, flight-ready galactic cosmic ray shielding system exists today. The problem is not merely unsolved, it is not close to being solved, which means any interstellar mission launched with foreseeable technology would expose its crew to continuous galactic cosmic radiation, with only partial mitigation at best. The cognitive degradation observed in laboratory animals would to some degree occur in the crew. The question is not whether, it is how much and how fast. And the honest answer, based on current evidence, is that the crew's ability to think clearly, remember accurately, and make sound decisions under pressure would measurably decline over the course of a multi-decade transit. Slowly at first, then faster as cumulative dose builds and inflammatory processes compound. The crew would not notice the change from the inside. Cognitive decline rarely announces itself to the person experiencing it. They would simply find, 1 year at a time, that certain tasks take longer, that certain problems feel harder, that certain repairs take more attempts than they used to. And all of this, the cancer risk, the neural degradation, the cognitive erosion, is only the radiation's effect on the crew's minds. It is simultaneously dismantling their bodies through mechanisms that interact with and amplify each other in ways that leave no organ system untouched. Galactic cosmic rays damage the cardiovascular endothelium, the delicate lining of blood vessels, contributing to accelerated atherosclerosis at rates beyond normal aging. They suppress immune function through direct damage to lymphocytes and bone marrow, leaving the crew progressively less able to fight infections at precisely the time when the ship's internal environment is becoming less controlled and more microbially hostile. They accelerate cataract formation by damaging the crystalline lens of the eye. They impair wound healing by targeting the rapidly dividing cells responsible for tissue repair. And in the absence of artificial gravity, which carries its own engineering mass burden, microgravity simultaneously causes bone density to decline at roughly 1 to 2% per month, muscle mass to atrophy, cardiac muscle to weaken, and blood volume to fall. These effects do not operate in isolation. They form a web of compounding vulnerabilities that tightens over time. A crew member who suffers a fracture from radiation-weakened bone must then rely on radiation-impaired healing processes to recover, attended by crew members whose decision-making capacity has itself been degraded by the same radiation, using medical supplies that are finite and cannot be replenished. Every medical emergency becomes harder to manage because the same environment that caused or worsened the emergency has simultaneously degraded the capacity to respond to it. The ship is not merely making the crew sick, it is making them less capable of treating their own sickness and less capable of maintaining the machine that is making them sick, all at the same time. The engine problem has a finish line. You build the engine, you reach the speed, and the propulsion challenge is behind you. The biological problem has no finish line. It runs for the entire duration of the mission, affecting every crew member simultaneously, compounding with every year of exposure, and leaving changes that no tool aboard the ship can reverse. The crew degrades alongside the vessel, and unlike the vessel, they cannot be repaired with spare parts. There is a particular kind of suffering that has no dramatic moment, no explosion, no rupture, no single point of failure you can point to and say, that is where it went wrong. It accumulates instead, in the background, beneath the threshold of daily awareness, invisible until the day it isn't. Psychologists who study long-duration confinement have a name for the environment that produces it. They call it a monotonous, restricted, isolated environment. The crews of interstellar vessels would have a simpler name for it. They would call it home. The psychological effects of prolonged confinement have been studied in analog environments designed to replicate, as closely as possible, the conditions of extended space missions without leaving Earth. The most ambitious of these was Mars 500, conducted in Moscow between 2010 and 2011, in which 6 volunteers spent 520 days sealed inside a simulated spacecraft, the approximate duration of a round-trip Mars mission. Shorter analog studies have been conducted in Arctic and Antarctic stations, submarine deployments, and isolated habitat simulations in Hawaii. Across all of them, the psychological data tells a remarkably consistent story. Confinement does not break people suddenly. It erodes them gradually, along predictable pathways, on a timeline that gets worse the longer the confinement continues. In the early phase of isolation, participants typically show elevated engagement and alertness. The novelty of the environment, the clarity of the mission, the social cohesion of a new team all provide psychological momentum. This phase fades. As weeks become months, dopamine and serotonin levels, the neurochemicals most associated with motivation, pleasure, and emotional stability, decline measurably. Depression symptoms increase in roughly linear fashion with mission duration. Sleep quality deteriorates as circadian rhythms lose their anchoring cues. Appetite changes. Social participation decreases. Crew members begin spending more time alone, in whatever private space a confined habitat allows, which is never much. The most critical finding for interstellar mission planning is not that these effects occur, it is when they peak. Across multiple analog studies, the period of greatest psychological instability began at approximately the halfway point of the mission, and intensified through what researchers have named the third quarter effect, a period of heightened psychological distress, interpersonal volatility, and behavioural disruption that occurs roughly 3/4 of the way through a confined deployment. Submarine crews experience it. Antarctic winter overteams experience it. The Mars 500 participants experienced it. It appears with enough consistency across enough different environments and populations that it is no longer considered a variable. It is considered a feature of prolonged confinement itself. Now apply this finding to a transit lasting 85 years. There is no meaningful halfway point the human mind can locate. The crew cannot see their destination growing closer in any perceptible way. They cannot see Earth receding behind them. Earth disappeared from naked eye visibility within the first months of departure. They are suspended in a void that looks identical in every direction, with no external reference point to mark progress. No seasonal change, no variation in light, no horizon that ever shifts. The third quarter effect on an 85-year mission does not occur at year 64 and then resolve. It has no resolution. The conditions that produce it are permanent. But the psychological burden of interstellar confinement goes deeper than the effects documented in analog studies, because every analog study ever conducted had one feature that an interstellar mission fundamentally lacks, an end date that the participants knew about. The volunteers in Mars 500 knew on day 1 that the simulation would conclude after 520 days. The Antarctic researchers knew the supply plane would return in spring. Even the most isolated submarine crew knew their deployment had a rotation schedule. This knowledge, the simple cognitive anchor of a defined endpoint, is one of the most powerful psychological tools humans use to endure hardship. Strip it away, and the nature of the suffering changes categorically. For the crew of a generation ship, the destination is not a place they will ever see. They will live their entire lives inside the vessel and die before arrival. their children may face the same reality. Their grandchildren will be further removed from any living memory of planetary existence, maintaining systems whose original design logic may have been partially lost through imperfect knowledge transfer, educated about a home world they have never seen and will never reach, in a social structure that exists for no purpose other than to keep the machine running long enough for someone else to complete the mission. No psychological framework developed from any human experience on Earth prepares a person for this, because no human experience on Earth has ever produced it. The social dimension of this confinement deserves its own examination, because it is not merely an emotional problem, it is an operational one. Human social groups in confined, isolated environments develop predictable dysfunctions over time that directly degrade mission performance. Cliques form and harden. Power dynamics shift in ways that undermine formal authority structures. Resentments accumulate from frictions too small to formally address but too persistent to forget. Communication patterns between subgroups degrade. The initial cooperative unity of a shared mission gives way, gradually and often invisibly, to territorial behaviour, social withdrawal, and chronic low-grade conflict that consumes time, energy, and cognitive resources that the ship cannot afford to lose. These dynamics have been observed in every long-duration isolation study ever conducted. They are not failures of character or crew selection. They are emergent properties of human psychology under conditions of sustained confinement, properties that appear regardless of how carefully the crew was chosen, how thoroughly they were trained, or how committed they were to the mission at the outset. On an interstellar vessel, these dynamics would operate inside a social environment with no escape valve. There is no taking a walk outside. There is no calling a friend on another continent. There is no quiet weekend away from the people whose habits have been abrading your patience for a decade. The same faces, the same voices, the same personalities, in the same space, for as long as any of them are alive. What makes this socially corrosive environment especially dangerous is not the conflicts it produces in isolation. It is the way those conflicts interact with the cognitive degradation being driven simultaneously by radiation exposure. A crew member whose prefrontal cortex has sustained cumulative radiation damage is less able to regulate emotional responses during interpersonal friction. They are more likely to interpret neutral communication as hostile. They are less capable of the sustained, deliberate perspective-taking required to de-escalate a conflict before it metastasizes into something that requires physical separation of crew members in a habitat where physical separation means being 12 meters away instead of 8. The radiation erodes the neurological tools needed to manage the social environment. The social environment generates stress that accelerates cognitive decline. Each process makes the other worse. Sleep sits at the center of this feedback loop in a way that is easy to underestimate. Chronic sleep disruption, which confinement, circadian drift, noise from life support systems and psychological stress all reliably produce, impairs every cognitive faculty that radiation is also impairing: memory consolidation, executive function, emotional regulation, decision-making under uncertainty. A crew member who is both sleep-deprived and accumulating radiation damage to their prefrontal cortex is not experiencing two separate problems. They're experiencing one compounded problem that is worse than either would be alone, and that no amount of sleep hygiene protocol can fully address when the underlying causes, the radiation, the confinement, the stress, cannot be removed. The pharmaceutical options for managing these psychological effects are themselves subject to the same finite supply problem that governs every other consumable aboard. Antidepressants, anxiolytics, sleep aids, mood stabilizers, all have shelf lives measured in months to a few years under optimal storage conditions. A mission lasting decades cannot carry enough medication to treat a crew of psychologically deteriorating individuals for the full duration of the transit, even if the medications remained potent, which they would not. The crew's psychological support system cannot be restocked any more than its water supply can. It depletes, and it does not recover. There is a tendency to assume that the right crew selection solves this, that if you choose psychologically robust individuals with the right personality profiles, the right conflict resolution skills, the right emotional resilience, the problem is manageable. This assumption does not survive contact with the data. The analog studies were conducted with carefully selected, professionally trained individuals motivated by genuine commitment to the mission. They still experienced the third quarter effect. They still developed interpersonal conflicts that required intervention. They still showed measurable psychological deterioration over time. Selection improves outcomes at the margins. It does not change the fundamental character of what prolonged confinement does to human psychology, because that character is not a product of individual weakness. It is a product of the environment itself, and the environment of an interstellar vessel is not merely as psychologically hostile as the most demanding analog study ever conducted. It is categorically worse in duration, in isolation, in the absence of any endpoint, in the knowledge that the people around you are the only people you will ever know, and in the additional burden of radiation damage accumulating in the neural tissue that psychological resilience depends on. The analog studies showed us what confinement does to healthy, unirradiated human minds over periods of months. An interstellar mission would ask what confinement does to progressively irradiated human minds over periods of decades. The answer to that question has never been tested. Based on everything the data suggests, it is not an answer anyone would find encouraging. Every system described in this video has been treated until now as its own problem. The radiation as a biological threat, the maintenance burden as an engineering challenge, the psychological erosion as a human factors issue, the water deficit as a chemistry problem. This framing is useful for explanation. It is misleading for understanding. Because aboard an interstellar vessel, none of these problems exist in isolation. They are threads in a single fabric, and the fabric does not fray at one point. It pulls apart everywhere at once, each tear widening the ones beside it, with no help coming from anywhere. Trace one cascade to see how this works in practice. A crew member whose prefrontal cortex has sustained 15 years of cumulative radiation damage makes a calibration error while servicing the water recovery system. The error goes undetected for 72 hours because the monitoring sensor has drifted beyond accurate calibration. Its semiconductor substrate degraded by the same radiation environment that damaged the crew member's judgment. During those 72 hours, the distillation membrane is exposed to conditions outside its operating parameters, accelerating the fouling, already reducing its efficiency. The replacement membrane, stored for 15 years in that same radiation environment, functions at roughly 85% of its original specification. Water recovery efficiency drops another fraction of a percentage point. The crew adjusts by reducing hygiene water allocation. The reduced hygiene increases microbial load throughout the habitat. The increased microbial load accelerates filter consumption in the air processing system. One error, and the ship is measurably worse off across multiple interconnected systems, in ways that compound forward into the next failure, consuming crew time already stretched thin across a maintenance schedule the ship was barely meeting before the cascade began. Nobody died, nothing exploded, the mission continues, and it is slightly more fragile than it was 3 days ago, in ways the instruments may not yet be sensitive enough to fully measure. Multiply that sequence across hundreds of subsystems over decades of unbroken operation. The vessel does not decline in a smooth, predictable curve. It declines in waves, each cascade triggered by the convergence of multiple degradation pathways, each one leaving the ship less capable of absorbing the next, each one arriving sooner than the last because there are more degraded components available to trigger failures and fewer reserves to contain them. Engineers call this cascading failure coupling. Complex systems in harsh environments tend not to fail gradually. They fail in accelerating pulses, each one wider and harder to stop than the one before, until the system receives external intervention or crosses a threshold it cannot recover from. An interstellar vessel never receives external intervention. Every cascade propagates through the full system and leaves permanent damage. The ship accumulates scar tissue, functional but diminished systems held together by improvised repairs and narrowing margins, each scar making the next injury more likely and more consequential. By year 40, the vessel is not the ship that departed. It is a degraded approximation, running on workarounds and contingency procedures, staffed by a crew that is itself a degraded approximation of the crew that departed, and the gap between what the ship needs and what the crew can provide is widening from both ends simultaneously. In the early years, the crew functions as a buffer against cascading failure. Their competence absorbs shocks before they propagate, catching problems early, extending component lifetimes through preventive maintenance, improvising solutions before failures compound. As radiation accumulates in their neural tissue, as confinement erodes their motivation and emotional stability, as sleep deprivation becomes chronic, that buffer thins. Problems are detected later. Maintenance is performed less precisely. The ship degrades faster, which increases workload and stress, which accelerates the crew's own deterioration, which allows the ship to degrade faster still. The loop does not have an exit. Success does not build momentum in this environment. It builds burden. The margin for error is widest on day one. When the ship is newest, the crew is freshest, and the reserves are fullest, and narrowest on the last day, when the most degraded systems must perform their most demanding functions: deceleration, orbital insertion, approach. Every interstellar mission architecture places its highest operational demands at the end of its longest period of cumulative degradation. There is no restructuring this. It is a consequence of what the journey fundamentally is. The proposed solutions each address one thread while leaving the rest to fray. Generation ships spread the biological burden across multiple lifespans, but the founding generation's children inherited a mission without being asked, and their grandchildren were born into a metal world they cannot leave, maintaining systems whose original design rationale may have been partially lost between generations, because no educational program perfectly preserves the tacit knowledge of the engineers who built the thing. Knowledge erodes across generations the same way components erode across years, quietly, invisibly, without announcing the gap until something fails that nobody aboard fully understands how to fix. Suspended animation appears to sidestep the biological problem, but hibernation does not make the ship maintain itself. Either a skeleton crew rotates through wakefulness, subject to all the radiation and maintenance burden described in previous sections, with a smaller team and higher per-person workload, or autonomous systems must manage the vessel for decades without human oversight, handling failure modes that cannot all be anticipated in advance, in a radiation environment that degrades their electronics continuously. The maintenance problem does not disappear when the crew sleeps. It transfers to a different set of systems facing identical constraints, with no human judgment available for the failures that fall outside the automated system's design parameters. Fast transit compresses the timeline but increases the energy of each particle impact on the hull, intensifying radiation per unit time even as total duration decreases. The benefit of speed is partially consumed by the cost of speed, and the life support systems still need to function. The crew still needs to eat and breathe and remain cognitively intact, and nothing about going faster makes any of those requirements easier to meet. What no proposed solution addresses is the fundamental nature of the problem itself, the interaction of all failure modes within a closed system that cannot receive external assistance, across timescales that exceed the design lifetime of every component involved, including the organisms operating them. Every architecture moves the problem, none of them make it smaller. If humanity does eventually cross the interstellar void, it will not be because we built an engine powerful enough to get us there. It will be because we solved something far harder and far less photogenic. How to keep a tiny closed pocket of Earth, its air, its water, its soil, its medicine, its social fabric, intact across distances so vast and timescales so long that simply continuing to exist becomes the greatest sustained achievement our species has ever attempted. Not the launch, not the arrival, the endurance, the 10,000th morning, the careful, unglamorous daily work of holding entropy at bay with finite tools in an infinite void. Reaching the stars sounds like triumph. Surviving the space between them is something quieter, something harder, something that doesn't fit inside a highlight reel. It is what happens after the cameras stop rolling and the ship is alone and the systems are aging, and the only thing standing between the crew and the dark is their own diminishing capacity to keep going. The stars are not the hard part. They never were. The hard part is everything that happens between here and there, every single day for as long as the mission lasts, against an environment that doesn't care whether they make it, and won't notice either way if they don't. If you like the video, don't forget to leave a like and subscribe. It makes a huge difference and helps the channel grow.